I was just mentioning to Bryce that the lava tubes, possibility of lava tubes to people in inflatable structures is more exciting in terms of the technical challenges it solves for us than the existence of water on the moon. So I'm really grateful to have been scheduled right after them. I'm going to say some very obvious things at first. This is going to be basically an introduction to inflatable structures. A lot of people aren't familiar with them. They may have heard about possible uses, but most people aren't too familiar with it. So I'm going to go over the why, what's, and hows. If that's too simple for you, I'll be doing a repeat performance tomorrow at 11 a.m. And if you'd like more technical information, details, and designs and whatnot, ask me after this, and I'll try to put that in for you tomorrow. Go ahead and stand it there. I'm going to say something right now, and I want to show of hands who's going to be surprised by this or horrified or whatever. And in a world of ever-shrinking resources, humanity's eye turns increasingly and necessarily to the limitless reaches of space. Anybody surprised? No, okay. Secondary is we can make all kinds of nifty scientific discoveries, but primarily we're looking at resources. Now, in order to meet these goals, we're going to take steps. Our first step is we're moving to the International Space Station, which will get launched someday, and is in the meantime producing a lot of artwork. And then hopefully we'll move to a permanent human-tended lunar base, followed by a human mission to Mars and a Martian colony. Go ahead. Now, a lot of people will argue with the point that we need a human-tended lunar base. Why bother? Let's just go to Mars. And Bob Zubrin will present his plan to do that, I think tomorrow, or he's doing that today, not sure. But personally, I wouldn't want to be on that mission to Mars if I hadn't seen all the hardware tested on another planetary base first. I mean, you can test all you want in Antarctica, but there's still an atmosphere there, so I'm not really willing to trust that. So the main function of a lunar base is going to be as a test bed. You have less communication time in case something goes wrong, less travel time, of course. So that's your precursor. You can test your life support systems, your manufacturing techniques. Then you can also make use of your lunar resources, which we've seen quite a number of papers on today. You've got your oxygen, there's water, metals, mass for radiation shielding of orbital facilities. And the moon is an unparalleled site for deep space astronomy.
Over there, the gentleman in back. You just unplugged us.
Oh, I did?
The far side of the moon is stable. It's quiet. It's shielded from radio interference from Earth. You can't get that kind of a platform anywhere else in the solar system. So now I've convinced you we need to go to the moon first. Let's talk about what we know about the moon and Mars. And we know a lot about both of them, but there's also a lot we don't know. But what we mainly know is that they're nothing like Earth. Right? You can't test something on Earth and say that's good enough for the moon or Mars. They're very different. The primary difference, and this is my only eye chart, everything else is pretty big, so if you can't read this, that's the only one. The main difference is this right here, your atmospheric pressure. None on the moon. Very, very tiny, 0.6 kilopascals compared to 101 on Earth. So that atmosphere on Mars, though it provides us with some resources, carbon dioxide and oxygen, it's very, very thin, so it's not providing any sort of pressure whatsoever. Another main problem on the moon is, of course, the day length. You have 14 days of darkness. It's cold and no solar electricity. Mars, this is a great number right here, 1.03, love that. Temperatures are a big problem. On the moon, it gets very, very cold, and it gets very, very hot. And on Mars, it gets very, very cold, and then it gets kind of nice. Radiation, we don't have a lot of information. I don't know if Pathfinder collected any data on radiation. I don't think so on Mars, so there really isn't a whole lot of data. How much radiation, galactic cosmic radiation, is getting through that atmosphere? Some people say, oh, it's attenuating quite a bit, you don't know too much about it. Other people say it's not providing any protection whatsoever. Same with micrometeorite flux. Now this number here, I just assigned it basically the same as what was measured on the moon. Probably not true because of, again, of the atmosphere. In the benign category, you don't have any weather on the moon. You don't have to worry about snow. You don't have to worry about wind. That's great. But you've got this horrible clinging dust that Bryce was talking about. And on Mars, you've got the wind blowing the dust all over the place. Now, the wind on Mars is not going to count as a structural load because your dynamic pressure due to that lower atmospheric pressure, it's like 100-mile-an-hour wind is going to feel like somebody basically talking to you. And you're not going to notice too much there. And then you've got the gravity, which is very nice. Reduced gravity, 1/6 g on the moon and approximately 1/3 g on Mars. And then on both the moon and Mars, you have a reduced seismic environment compared to Earth, but we're not exactly sure on Mars. Okay, so if you want to go to the moon or Mars, the first thing you need is a life support system to live in, and you need a structure to house that life support system. So what are the main drivers of your requirements for your lunar structure? Number one is that no external pressure. You have to deal with that. So you're going to have to pressurize it, and that is making any structure, whatever structure you build, a pressure vessel. You can't get around it. TD was talking about his concrete structure, and he had ways of bracing and reinforcing that structure so that it could support pressure. In our analysis, which I can go into more detail tomorrow if you like, the maximum tensile stress in an inflatable structure that's pressurized is up around 650 megapascals, and TD's concrete had a tensile capacity of 8 megapascals. So, and it's a big leap to go to a concrete structure. So the main point that you have to remember is you are a pressure vessel. Whether you're made out of aluminum, whether you're made out of concrete, whether you're made out of whatever, you are a pressure vessel. So from there we can go on to defining more detailed requirements. And the first of those is this structure better sustain all your loads. Right? That seems fairly obvious, right? So let's focus on that. Also, we want it to be durable and reliable, obvious. We don't want to have to inspect it, make repairs, too much maintenance, takes too much time. It has to support all required operations. You don't want a structure that's good for some things, but not so good for other things. It's a waste of time, it's a waste of money. So you want something that's really generic. And of course, you have to make provisions for your life support systems. Okay, I'm gonna, in your design and construction requirements, first of all, inflatables are most beneficial because you can stuff them up into little boxes and they're very lightweight to transport. So small stowage volume and light mass, that's one of your main requirements. That's why you like inflatables. The material issues in inflatable structures are right now, they're the key issue facing the inflatable structure community, and this is something that we're addressing at Colorado State University. People are all over the country and all over the world are looking at these. And the design requirements are sometimes conflicting. For example, if you want something with a high puncture resistance and a high stiffness, those two requirements can be counterproductive. And also if you're for easy stowage and stiffness. So you have all sorts of conflicting requirements. Also very important is the air permeability of the membrane. It's expensive. Air is heavy. You don't think about it, but air is heavy, and you don't want it leaking out through your membrane. So that's another big one. All right, let's go to the next slide. Just a couple of other requirements. You don't want it to be too difficult to deploy. You don't have a large workforce. You don't have a lot of equipment. You want to be able to use robotics wherever possible. You want to be able to set it up and connect it all easily. Now, integrated foot pads, that's so you don't have to go in with a backhoe and the bulldozer and make everything nice and smooth. You just want to be able to set it up wherever you are. And the last one, let's just cross that one out. Say we're going to live in a lava tube. Forget it. We don't need that one. No. Well, once we have firms say here's our lava tube, then I'm gonna take that one off, and very excited about it.
And you can put an inflatable inside a lava tube.
Absolutely, absolutely. As a matter of fact, there's one of the displays in the exhibit hall shows that. Okay, so let's talk about our structural loads, because that was our first requirement: sustain your loads. I have up here 10 psi. Now, NASA works with a standard sea level atmosphere of 14.7 psi because they live in Houston and they can't imagine how anybody can survive in less than 10 psi. Well, I live in Colorado and I say, you don't need that. Reduce your load on your structure by 33% by reducing it down to 10 psi. On the moon, you don't have to use air with 21% oxygen. The important thing is that for human physiology is that your blood is saturated with a certain amount of oxygen so that you can perform at your best. Well, all you have to do is up the oxygen content a little bit, and you can reduce the load on your structure by 30%, up the content by only 5%, and so you have 26% oxygen. Your fire hazard hasn't increased too much, but you're breathing just fine. So we've been using a design reference of 10 psi, and that's my story, and I'm sticking with it. So I talked about gravity. This is great. You don't have to worry. Your structural loads go way down because of these gravity coefficients. Let me see, I had something different. So gravity is our friend on the moon and Mars. Your live and dead loads. Now this is compared to, say, design loads for a building on Earth, and then we just scaled them down for gravity. So they come out to be less than 1% or up to almost 2% of your internal pressure. So this is still going to be your dominant structural load in designing a structure. And then Regulus shielding load, which if you have a structure on the surface and you want to put the Regulus shielding load on it, that's counteracting your dominant internal pressure load. So that's a happy load anyways. We don't have to worry about it. It's not putting too much pressure on. But for today, let's just assume we don't need it because we're all happy about lava tubes. And I'll talk about framing system pressurization. You don't even know what that I'm talking about there yet, so let's ignore that for now. Okay, so if you were to go up to your friendly neighborhood Mongol horseman and ask him the question, what's the best sort of structure for moving in real fast, setting up real fast, and tearing down and moving quickly? And he's going to answer you, tensile membrane structure. Actually, he's going to say yurt, but you and I are going to know what he means. So what he's really saying is something made out of a thin membrane that can be deployed rapidly, broken down rapidly if necessary. And the same as with, okay, you're going backpacking. What are you going to take with you? A tanker container, some sort of shipping container, or a tent? Okay, so it's the same concept. An inflatable structure made out of a thin membrane is the ideal pressure vessel in terms of the minimum amount of mass to carry the structural internal pressure loads. And so you've got a low mass, and in terms of space launches, mass equals money. And this thing could be made out of spun gold. It doesn't matter how expensive your material is. That mass equals money. So that's your number one benefit right there. Also, you got the small stowage size versus your deployed volume, and your deployment requirements can be minimized through controlled pressurization. So how do we go about designing an inflatable structure? The first thing we have to do is pick out a shape. Now, the ideal pressure vessel shape is a sphere. It's doubly curved. It's in tension everywhere. It's the most efficient pressurized volume. But it has some other problems. Like, for example, how do you make fully efficient use of that interior volume? Well, you have to put in multiple floors, and it gets kind of difficult to set up. Also, covering it with regolith, assuming you have to cover it with regolith, can be kind of difficult. So we don't really like the sphere. Now, cylinder is slightly less structurally efficient, but it's a little easier to work on. NASA is working with cylinders down at Johnson right now, working on an inflatable cylinder for and the International Space Station is going to test there, and then they're hoping to use it as a Mars transat. So they like cylinders. Now, architects, if you go out to the exhibition hall and you see the display from the University of Wisconsin from their architects, they're showing inflatable habitats inside what I believe are lava tubes, and they have flat sides. And the reason for that is that architects like square sides. It's easy to put stuff in square sides. That's what we're used to. But you can't have a pressure vessel with flat sides. It doesn't work. So you take some sort of prismoid structure, which is a combination of spheres and cubes, and you put it together, and you come up with a sort of a modular shape like this, where your floor and your ceiling are segments of a sphere, and they're bounded in a vertical plane by arches and columns, and the walls are prismoidal. They're approximating a sphere. So this is the design that we're working on at Colorado State, and it's our reference structure. Now, we're not saying that this is the ideal shape, but we came up with a number of requirements, and this is how everything fell out. There's 400 square feet of floor space inside of each one of these modules, and the reason for that was we wanted it to be large enough, similar to a common terrestrial workroom, and that is for that functionality for all base operations. You know, you should be able to do almost anything you want to do with 400 square feet of space, and if not, well then you'll put them all together. Let's just very briefly put that one up there, and I'll go over it.
That has been fabricated. It's actually being studied now.
It has not been fabricated. This is all computer models, and I'll go over the simulation right now, and I'll talk a little bit about our materials development, probably. I don't know if today I'll get to it or tomorrow. So again, you've got your spherical roof and subfloor, your arches, and columns are cylindrical, and they are pressurized. Now, we did a study of 3 different options for the framing system. One was graphite, epoxy, or titanium tubes, rigid tubes, or foam-filled members, or then these pressurized members, and the structural analysis showed that the pressurized members were, one, way lighter than any other option, and they did the job. They carry the load. They raise a whole host of materials issues because the pressurization needed to support the structure when it's depressurized on the inside is huge. It's 900 kilopascal, 130 psi, so you have some safety issues and some materials issues. But those things they're coming out in the wash. Everything's the structural analysis using the Kevlar fabric assumptions we had. It worked. So nope, that's fine. Okay, a lot of people say, why are you bothering with this framing system? The number one reason was to hold this prismoidal shape, and that's something to form this. The module is basically a cube, which architects like, people like. It's easier, it's very functional. So the framing system holds it into that space, allows it to be connected to other modules. You add as many as you want, whatever you need. You can put your foot pads for deployment wherever on the bottoms of the columns. You have support points for internal fittings. And if the interior of the module is deflated and you have a regolith cover, it'll hold the structure open, and of course to join adjacent modules. So this is a little cartoon, and we won't nitpick the various inconsistencies of this drawing with what we now consider to be reality, but you say you want a lunar or Martian base, take a bunch of modules, you put them all together, you set them up, you cover them with regolith, or put them in a lava tube, and you're ready to move in. So in our modeling work that we have done, we have been making some broad assumptions in terms of material properties. And the first one was that we'd be using some sort of Kevlar 49 composite in a neoprene matrix. And the main reason for this was that it's been flown. The instep inflatable antenna beams and the supporting torus was Kevlar neoprene. It's available, it's worked, the properties are known, so we used it for our model. And these are just some of the material properties that we assumed. And the main reason we wanted to make these assumptions is because we wanted to be able to give NASA some definite numbers. How thick are the membranes? How heavy are the membranes? You know, what are you giving us here? So what we did was we created, an integrated computer simulation where we took a finite element analysis and we merged it with a 3D graphic model, and that gave us the numbers we wanted to give to NASA, and it also gave us pretty pictures to give to NASA, which, as everybody knows, is one of NASA's favorite things. And finally, it allows us to go on and optimize the module design, which, as it turns out, was a little premature because until you get the material issues solved, there's no point in optimizing a design for a material that doesn't exist. So what we found, assuming you're using this Kevlar neoprene, and Kevlar is not going to be the fabric. It's got all kinds of problems with stowage, with ultraviolet stability, with abrasion resistance. So it isn't going to be Kevlar, but it's going to be something that's as strong as Kevlar and as light as Kevlar, but with a bunch of other properties, unobtainium. So our thicknesses, as you see, 25 hundredths of an inch, 15 hundredths of an inch. to support the internal pressure load of 10 psi with the regolith cover and with the 130 psi inflation of the framing system. These were the thicknesses that did the job. And the masses of the membranes for roof, subfloor, and all 4 side walls only came out to about 280 pounds. So it's extremely light compared to a similar volume, similar sized rigid structure. Okay, go ahead. And then the framing system, we calculated the mass of the air needed to inflate the framing system because we felt that that was going to be a driver, and also the mass of the membranes. And the total mass for the framing system came out to be 571 pounds. Now the total mass for a module is 385 kilograms or 850 pounds for a single module, providing you with 400 square feet of interior space. So that's about it for the definition or for the description of the module. We've got a couple little pictures, your module cluster, and actually my main pretty picture that showed some interior outfitting disappeared. I don't know where it went, but you can see it on our website. And we've been talking a lot about connections. Is the module truly identical, or each module is truly identical? If you look at this picture, they're not. See, they're sharing, where they join, they're sharing a column. So right now, we see the manufacturing of this as, say you have an initial need for your base. I need X number of square feet. So I take that many modules, I manufacture them all as a single unit, I send them up. Later on, if I need more space, I put some sort of air tunnel between them and add another cluster. So that's basically how we see that happen. If you're looking for more information, our website has publications, pictures, and contact information. And
I could see if you pile regolith on top of it, it would work, but if you want to go inside a lava tube, how would you keep the thing from blowing up?
Well, the membranes are strong enough to support the internal pressure load without the regolith cover on it. Now, if you're talking about anchoring the structure down,
Well,
or,
no, mainly just inside the lava tube, you don't have anything holding.
yeah, you don't need anything to. You don't need the regolith cover
If you had
to
a
equilibrate the
puncture,
internal pressure
something
load.
you'd go, that's about it.
You know, just kind of picking up material that doesn't go poof.
Yeah,
Make
well,
it strong enough.
yeah, you can make the membrane strong enough to withstand, say, a human-inflicted puncture. The main puncture damage is from micrometeoroids. If you're buried under regolith or if you're in a lava tube, then that's not so much of an issue. And right now, we're writing the qualitative requirements and sending them to an actual material manufacturer. And one of the main issues is this puncture resistance. And so the question is, do we make the puncture resistance requirement high enough so that it could resist an incoming micrometeoroid, which is like 1 centimeter, and it's moving at 20 kilometers a second, so it's really hauling. And or do you just say, well, I just want it to be like, have the same on the order of puncture resistance that's required for terrestrial inflatable structures such as life rafts, which is very important. They can't be punctured. And the issue is, if you put this thing up on the surface, then you have a period of time before it's covered with regolith where it's vulnerable to micrometeoroids. But if you put it in a lava tube, then you don't have to worry about that period of time. So that, like I was saying to Bryce, in terms of the technical difficulties of developing the material, putting in a lava tube solves a lot of problems. Like abrasion, how you're piling this stuff on there, it's abrading your surface, and that's horrible for your chemical stability. So, and lava tubes solve a lot of problems.
You mentioned, excuse me, when you want to add another module, you put in a tunnel and add on another module. If you use Kevlar or something similar, how easy is it to cut the hole? How easy is it to seal the tunnel at the either end?
Well, membrane to rigid fittings have been done. I mean, if you look at an Apollo spacesuit or any spacesuit, it's an inflatable structure with rigid metal fittings. So it's been done. The actual how do you manufacture a cluster so that it can be expanded onto? And that's one of the issues we're facing right now, which is why the optimization of the module itself stopped, because we were faced with exactly issues like that. And we don't know. How do you prep a membrane, so that someday, so right now it's structurally adequate to support this load, but someday you can cut it open and put it in this
Well, what you do is you just make a big old metal ring there that's all covered over and take the
grommet,
metal ring.
pre-grommeted or something like that, so I'm not sure.
I almost hate to ask, but what are live and dead loads?
A live load is a person walking through a room, and a dead load is a file cabinet.
Did you look at anything other than a 20 by 20? Because, no, given that the lava tubes are so big, did you look at like a multi-story single unit?
No, we have not personally. We're working with our one little module, and we came up with those dimensions because it seemed the minimum amount of area you might want to have, but easily expandable. And we didn't want to look at multi-story, multi-level, because that raises all kinds of deployment issues and outfitting issues. So we didn't want to deal with that.
That's why the historical work, there was a airlock that was originally constructed for Skylab, never flown. There was also a daytime extension module for Apollo, also never flown. And there was one system, they had a nickname for it, Moby Dick. I think it was a kind of design aimed for a shuttle at one point, but it was a huge cylinder.
I'm not familiar.
On the desire for larger inflatables, multi-story structures and so on, when you get to that size, you get into the realm where it is possible that you might want to be turning to lunar resources for the materials themselves. Dr. Goldenworthy's lunar glass, spinning it and weaving it into modules and so on, and larger size structures that you may not have to optimize nearly so much, simply because you don't have to haul them up there.
Yep.
That might be much better than working your tail off to get multi-story structures down here,
Right.
two up there.
Mm-hmm. Yeah, if you look at lunar-based development, you can basically put it in 5 stages, and the names of the 5 stages change with who you're talking to. But basically, they consist of an exploratory stage, your robotics and everything, going checking things out. Your pioneering stage, things like Apollo missions, you go up, you stay for a couple of days, you come home. Your outpost stage, where you've got a permanent base, a small crew, and then your settlement stage, where you got some more people, and then your full colony stage, which is a lot of people. If these inflatables, we're aiming at the outpost stage. So they're too far advanced for something in a pioneering stage, but we don't think they're significantly advanced to be used further on down the line when you're talking hundreds of people or thousands of people. So yeah, but in situ resources, that we'd expect those to come into play in those 2 later stages. Yes?
Do you see a need for continuous monitoring of your skeleton framework, the pressurized framework? Or do you think you can pump it up and then just walk away from it? Your leakage rate is going to be so low that...
Absolutely not. But I don't trust anything. Monitor everything. The thing is while the module is inflated, it's holding the structure up. That pressurized framing system isn't doing much of anything, and it's only really necessary when you're deflated. I mean, the fact that the membranes are there. Can you put up the little sketch of the module? No, that it's way back. It's one of the first.
One of the first ones.
Yeah, a little sketch with the pointers to the various, exactly that one. Oh, no, sorry. There we go, that one, yeah. Okay. So while you're pressurized, see that internal web right there? Basically what that is that's your load path from your roof to your sidewall. It maintains your continuity of your membrane. And once the interior of your module is blown up, you could probably just, if you weren't too concerned about a sudden emergency depressurization, unexpected depressurization, you could depressurize this framing system, and that web will hold your shape. And if you had a planned depressurization, then you could inflate the framing system. Or if you had some way of inflating it really, really fast, in the case of an emergency, then you can deflate that too. But to answer your question, no, I would never leave anything unmonitored. And is that it? All right, well, thank you very much for your time and attention.